You don't see ellipses. If you don't see ellipses, I can't even continue. See? See the ellipse?
Yeah.
Ellipsoid.
Well, it's a section of an ellipse.
Ellipses are something you're not supposed to see, right? That never
Yeah, exactly.
So the requirements for listening to Randy's talk is to be able to say the title 5 times fast. Smectic topology, topography, and tomography, Randy.
Thank you. Well, I'd really like to transmit information today, so please slow me down and ask questions. That would be the ideal solution. The ideal result would be that information transmitted. And like I said already in the initial quiz, here are some ellipses. And I'm going to tell you about these materials. These are smectics. I'll tell you what smectics are. And I'll tell you that it was a triumph of 19th century mathematics to see this in a microscope. This is like microns. This is not so small. You can see this with a magnifying glass or a microscope. To figure out what this structure was without having, you know, X-rays or electron microscopes or particle colliders or anything like that. So, let me start. Let's see if this works. It should work. Oh, there you go. I want to show you a movie, just to get you in the spirit of the thing. This is Ponlevé's son. Of course, that follows. He obviously was Ponlevé's son, but the Ponlevé you're thinking of. Okay. So. There's music if you care, but that's not important. This was made in the 60s, of course.
And will you tell us what's happening?
No, I can't. It's very complicated. But what you're looking at is you're looking at liquid crystals. Smectics are one of the phases of liquid crystals. Liquid crystals are the things in your computer displays. Maybe I can make it. And what's happening is this liquid crystal is on a metal plate. So they're looking at a microscope, they're looking down at the liquid crystal. There's a metal plate behind it, probably copper, right? And they heat it up in different places. So now you have heat gradients. So you're going through different phases of a liquid crystal. And they change very rapidly. This is a smectic phase. I know that because somebody told me, all right? And you can watch as it's going. It's coarsening. And wherever you see dark, it's isotropic. It's completely melted. It's the melted phase of the liquid crystal where there's no order. Alright? So I want you to get the idea. These are the kind of real things you see. Okay? And the real things you see are really quite complicated, but kind of, these are not bees. Right? Look at that one. I always see the bee is telling me, go 100 miles, this 100 yards that way, turn left, right? There'll be a flower pot. Okay? Here you get, so again, now you see now you see ellipses, and they're coarsening, something's happening, they're moving. It's very complicated. So you could try to be, you know, Mike Shelley, who's giving a talk right now in physics, and you can try to simulate this and do the numerics carefully and understand what you're seeing. But I look at this and I wonder, I don't even understand what the constituents are. Can I explain this? Can I explain this to Herman? Can I explain this to my students? Right? How about to me? Right? Can I understand just for myself what this is? This is about the only one I know what this is. This is a dark phase and some other phases growing out of it, and these little spherulites, little drops are growing out, droplets growing out. But then there's another third phase that's coming in. It's doing that dendritic thing. It's a different phase of matter. So let me go on with that picture. You can Google it. You Google Ponlevé liquid crystal. There it is on YouTube. Okay. So liquid crystals. What are we seeing in these pictures? These bright, colorful pictures. Gareth showed this slide some time ago. I've lost my pointer, but I have this. It'll come up. So, what do you see? There's some backlight. What happened to it? It's in my pocket. I had a laser pointer. Oh, it's here. Okay, there. All right. Okay, so here's the light. There's a backlight. Here's a polarizer, like the things in your sunglasses, right? Here's another polarizer that's perpendicular to it. What do you see if you shine a light through two polarizers like this? What?
Black.
Excellent, excellent. But you notice that you don't see black all the time. Because there's stuff in there. Those molecules change the orientation of the polarization, and so you can actually detect what's happening just by looking at the pictures under cross polarizers. It's a very simple setup, right, that anybody can do. So there are these phases.
What does rubbed mean?
Oh, it means that the molecules on this side, the way they make these real displays is they take this glass polarizer, they spray it with some kind of gunk. It's actually like Pam. It really is. It's like the spray Pam. And then they take a napkin and they go, all right? And then magically, all the molecules, when they're on that surface, they point the same way as the polarizer. Or they point the same way as you rub them. Okay? Nobody understands. Here's interesting. Nobody understands. You can rub really gently this way, and then you can rub hard this way, and then rub gently this way. And it only cares about the last rub, not the hardest rub. Okay? This is when I say rub, this is really how, you go to, what's that company? Samsung. This is really how they do it. I mean, it's important science, it's important technology, but why it works is a mystery to a lot of people. Even to the people who use it. So I told you there are these phases. So far I've said 3 phases. Those are the only 3 phases I'm going to talk about. There's the isotropic phase, the pneumatic phase, and the smectic phase. These liquid crystal systems are made of these long kinds of molecules. Long molecules, which I'm now going to idealize as just lines. The long molecules, you do like pickup sticks. You know that game, pickup sticks? Right? I never understood the point of it until I got older, right? So you throw them down on the floor, and the sticks all point in random directions, and they also don't form a lattice. Right? They're not periodic. There's no order to where the sticks are either. The pneumatic phase is a funny phase. It's the phase that you use, it's the way you win in pickup sticks. Alright? In pickup sticks, the way you win is you get them all to point in the same direction. Right? And then you go, you pick them up, and you pick up a lot of sticks. If you can orient them so they're all pointing in the same direction, you get a huge bundle of them. Okay, it's the principle behind the chalk dispenser, okay, for instance, or boxes of chalk. That's the pneumatic phase. Again, there's no special order of the rods. Right? The rods aren't oriented, their positions are not in any special place, they're just oriented all the same way. Finally, the smectic phase. The smectic phase is a solution to our parking lot 2, right? Which is, it's better to park in rows. Okay? You park in rows, then you're in even better shape still. Even if it's like this. So it could be that you have, here's somebody's SUV, and here's somebody's smart car, and here's a motorcycle, right? And here's a bigger car, and a smaller car. It doesn't matter whether this row is nice and ordered, pop, pop, pop. But even if I were parking different sized cars, I would still get more space and be able to pack more efficiently by putting them into rows. As opposed to letting this guy jut out into the next row. Right? One guy jutting out messes up the whole thing. So this is the smectic phase.
But could in the smectic phase, the top rows point this way nicely, and the second row point that way nicely?
Yes, that's called the smectic C phase. Excellent. Right, or the antiferromagnetic smectic phase. Sure, you can have all sorts of extra patterns, right? Extra discrete symmetries on the panel. So, it's okay. And Gareth showed this picture a few weeks ago, if you recall, where what he showed that if you were looking under cross polarizers and you're looking at a texture like this, what would you see? Well, you see these brushes. See, mine look more like brushes. Herman asked, why are you calling them brushes? Because they look like brushes, right, in the pictures I drew. So what did I just do? I blackened out all the places where the molecules were along the polarizer or the analyzer. If they're along the polarizer, then nothing happens to the light. It comes out that way. If they're along the analyzer, nothing happens to the light. And you get black. And you can do this again for the other ones. And you get these brushes. Ooh, brushes. Okay, there you go. The last set of brushes.
Could you get one, let's see, could you go?
Yeah, sure. Perfect. Or you want me to do it again?
So the brushes were horizontal lines in the upper left picture.
Yes, so I'm gonna throw out the pre-image. The pre-image of up and down or left, right is gonna be black.
So verticals and horizontals.
Exactly, so that gets blacked out. Here, it gets blacked out. Here, the same way. Here, the same way. And what am I seeing here? Why do I see 4 brushes? I see 4 brushes because when I have 4 brushes, it means that I've gone around the polarizer direction twice and the analyzer. I've passed through the polarizer direction twice and the analyzer direction twice.
As you circle around.
As I go around the thing. And so I can see the index of this line field. The index of the line field here is 2 pi. I don't know how you want to count it. 2, 1. I'll say it's 2 pi. I'll say it's a +1 defect. Of course, if it's a line field, I can have a half defect as well. Right? In the case of a line field, I don't have to come all the way around 2 pi, right? Because it's a line field. It doesn't know head from tail. And you can actually have plus half defects. Here they are. So here's that picture, this texture. And here you go. So I can focus on this or this. But I think you guys all know this, right? So I'll talk about this. Here you go, right? What would be the point of talking about topology here? So, here's the liquid crystal. Black is where I have those, where the lines are along the polarizer or analyzer direction. And these points in the center are the zeros of the vector, or the line field. Places where it's ill-defined. And I can see that I have 4 come out, or 2 come out. 2 come out means I have a 1/2 defect. It goes through the polarizer direction once and the analyzer direction.
Should we think of the stuff between the polarizer and analyzer as sort of 1 molecule deep, so there's sort of 2-dimensional array?
No, it's quite thick. It's like, it's you
And
know,
how would you get
microns.
any dark areas? Because if you go on a straight line and you polarize the analyzer, sure, there'd be some that are twisted.
That's right, but this is a situation, so yes, you could think of it as 1 molecule thick. Certainly elastically, it's as if it were just a 2-dimensional system, if that's the question, that's right. So, you get 4s, you get 2s. Here's a quiz, all right? Here are the cross polarizers. You can't tell from this picture whether this is going around +2 pi or -2 pi. Agreed? How could you tell? What would you do to decide if it was plus or minus? You're allowed to touch it. It's an experiment. All right? You're allowed to do something. What would you do?
Flip the polarizations of the different place.
Say it again?
Reverse the polarizations of the...
I would still get 4 or 2 brushes, but you're on the right track. Rotate them. If I rotate the polarizer and the analyzer together, the positive ones will rotate with me, and the negative ones will rotate against me. Yeah, so you can tell right away. You just have to do a little twiddle, and you're done. You just need 2 pictures. Okay. You can also have higher charges. So, for instance, if you just counting brushes, here there are 6 brushes, so that's plus or minus 3/2. Here there are 8 brushes, plus or minus 2, plus or minus 5/2, plus or minus 3. And what's neat about this is not just that you can count the brushes, so to a regular audience, I say, see, I've turned this complex liquid crystal texture into just a counting problem. Right? That's the essence of topology, right? Is that you just count. Right? And the number of arms, whether I'm nearby or far away, the number of arms are going to stay the same. Right? Until, the arms can rejoin and do other things later on, but as long as I avoid any other zeros, right, the number of arms coming out of this zero stays the same. And that's an invariant, and as the system evolves dynamically and smoothly, those stay until some catastrophic event happens and 2 of these zeros crash into each other. The other thing that's nice, at least in the pneumatic system that I'm showing you, is that in the pneumatic system, you can just add things. So you might say to me, I don't buy it. I don't really think there are 12 lines here. It looks to me like there are 3 lines here and then there are 9 lines there. But so what? As long as I go slightly further away than the resolution of this, that's only because I blew up the picture. Right? If we had bad eyes or a bad microscope, it would look to you like there were 12 coming out. So I could take something where I have 3 lines and 9 lines, or 4 lines and, I could say it's 4 lines and 10 lines. And I could bring them close together and replace the whole thing with something with 12 lines. Okay? So I can just add the charges of the zeros. Again, not very surprising. So this is the nematic phase, and this is what is interesting to me about the nematic phase, that you get these defects, and that they just turn some complicated texture into counting. Okay. So here's the Smectic phase that I told you about. One where you have these nice layers, like so. So you have this layered system. It could be layers of molecules. It could be oil and water, right? So this is what your cells look like. This is your cell membrane. So they can be like ice cream sandwiches floating in water. But again, just like I showed you in the movie, this is not what you see. All right? It takes great effort to have our experimentalists to make something that looks like a parking lot. What most experimentalists do is they look at this. They see this. They look under the microscope and they see something incredibly complex, which has extra discrete symmetries in it. There's some kind of other pattern going on that's beating, that's making it have this kind of interesting texture over here. This is one material making this very complicated pattern. And again, for me, if I try to understand the pattern, I want to understand, can I even understand it on the simplest level of counting? Can I look at it and say there are defects? This is built out of things, pieces that at least I can understand. All right, and since this picture and the picture that Nietzsche would have taken 5 minutes later will look different, but will also look the same. 5 minutes later, this thing will still look like a silvery blob with all these interesting patterns, but it will be a different silvery blob with interesting patterns. So I want to be able to make some kind of measurement or description that doesn't depend on exactly when Nietzsche took the picture. Okay. So Smectics have a different kind of defect in them. And these defects are known to some people. I think they're most common in, I don't know, probably here. The medical school probably has these defects. As an example. Here it is. Smectics have these, the medical school has this defect. Sometimes you have a pre-war building, right? Pre-war building on this side, and you build a new building, you get money from somebody, right? And the donor wants a 10-story building because, you know, that should be a 10-story building. But you only have an 8-story building to connect it to. So what you do is you make extra floors in the middle, right? This is the most common one, where you have 4 stories attached to 3 stories. Okay, what's this story called? So at the bottom one you could call 1, and you call this 2, and you call that 2. You call that 3. What do you call this one?
The mezzanine.
Exactly. That's what they do. You know, anytime they have to join them, they call that extra one the mezzanine. Okay, and so you get this extra floor, and this is just a defect. It's a defect exactly the same way. There's a counting thing. I can count as I go around this circuit. I go around counterclockwise. I go around, and I count now how many layers I pass with direction. Right? So here I go around, and I go up 1, down 1, down 1, down 1, down 1, and I'm back to where I started. So apparently I've lost 2 layers, or added 2 layers, depending on your sign convention. This is the same object with a different geometry, and then this is one where I only add 1. Okay, now again, now you can see these are maps. How do I describe this? These are going to be maps from the plane minus some puncture. There's going to be some place where I can't define the number of layers exactly. Here it'll be somewhere here. Here it'll be somewhere there. To S1. Why S1? Because these structures by themselves are periodic. So all I need to give you, if you like, is an angle, right, that runs from 0 to 2 pi, and each layer sits at 0, 2 pi, 4 pi, 6 pi, and so forth, and these are just phase slips where I've inserted an extra 2 pi. If I have a line field, then I can just insert an extra pi of phase. Okay? Is everybody getting this? Yeah? Okay. So let's think about the space of ground states. So every time I have my Smectic, right, here's my Smectic, right, well I can do a bunch of things to the Smectic, right? One thing I can do is I can shift it. You see that? Yeah, I can shift it, right? If I shift it by one layer spacing A, I get back the same structure. So 2 ground states, 2 pictures that are shifted by A are completely identical. If they're shifted by A over 2, they're, of course, equivalent, right? But they're not identical, right? They're equivalent but not identical. Shifting by A is identical. Likewise, I can take the direction and rotate them. And if I rotate them by pi, I get back to something again which is identical. And any other rotation is going to be equivalent, but not identical. So, I can say every possible ground state, every possible way of drawing a set of parallel lines is going to be somewhere in this manifold, right? So I have this manifold, or this space, I don't even know if it's a manifold. It probably is. I have this rectangle. It's a rectangle, all right? The coordinates here are the shift in the phi direction, the coordinates here are the rotation, and then I fill it in, and I already have drawn these pictures, and you already know what they mean. That, in fact, the way this thing's connected up is not like a two-torus, but it's a Klein bottle. And it's connected up that way because if I shift and then rotate by pi, that's the same as shifting backwards. And again, for the Klein bottle, if I talk about this being the shift direction and this being, say, the flip direction, you discover just from the picture that the homotopy group, right, the fundamental group of the Klein bottle is Nonabelian. And the fundamental group is exactly what we've been talking about, right? It was counting how many times I went through the polarizer analyzer direction. It was counting how many times I crossed a layer with sign, right? So I was exactly worrying about, when I talked about pneumatics, when I talked about the defects and Smectics, exactly the group operation on the fundamental group. And now I have this funny thing that the fundamental group isn't abelian. So that suggests that these two kinds of defects, one's about rotations. I would see that with the cross polarizers. If the Smectic rotated around 2 pi, and I had cross polarizers, I would see 4 lines coming out of it. Right? Because the molecules go around. That's the rotations. And then there's the translations. And the translations are the other thing. That's counting the layers, counting the floors, finding out if there's a mezzanine. So, here's a quick review of the homotopy theory of topological defects. So the materials are topological. In the materials, we call them topological defects. They're these holes, which, if everything evolves smoothly, the topological charge stays constant as I'm watching them. So what do? You have your sample, right? The base space. It has defects. The defects are holes in the sample, a place where you can't define the order. And then you have your ground state manifold. Here it's the Klein bottle again. And what you do is you look at maps from the fundamental group of the sample to the fundamental group of the ground state manifold. And those maps completely define the kinds of topological defects. And so I can talk about maps here. I go around this. If I focus just on one particular loop, a loop that goes around one defect once, then I can talk about all the possible non-trivial loops over here in the ground state manifold. Those are the stable topological configurations of the sample. Okay? And here's a presentation of the group is unaddressed. Right? Of course, I'm allowed to take this defect here, take this defect here, and I'm allowed to slide it around willy-nilly on here. What that would correspond to in the pictures is just rotating my coordinate system, doing one of these smooth deformations. So I don't actually care about the fundamental group, I actually care about only conjugacy classes in the fundamental group. So that's an important subtlety which I can say here. Usually I say it's an important subtlety which I won't talk about. Alright, so here's this important subtlety, which is important, right? So I look at a particular conjugacy class here, and then I look at the free homotopy on the target space. So here's a funny example of how these two things interact in this weird non-abelian way. So look at this picture here. Slide B. Picture B. This is a flip. You see how this is a flip? Here are the layers. Over here, way out here, way over here, the layers are going pop, 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 pop. They're going up.
Which of the 3 pieces should we be looking at while you're speaking?
B.
B. It's one flip. So A out here, it's pointing up, or it's pointing down. You pick, I don't care. We'll say it's pointing up. As I go around this line, the layers slowly rotate. So at each snapshot, if I just focused in right here, and looked in this little small square here, I would see parallel layers, but pointing in a different direction in that ground state manifold. And slowly, as I come all the way around, I discover that I've gone from something that was pointing up to something that was pointing down. Now they're equivalent. They're identical. So that's okay. That's a closed loop in my ground state manifold, right? It's in the homotopy group. It's in the fundamental group of my ground state manifold. But then what I can do is I can do something funky. I can take it and tear it. So now what I can do is I can add it, I can say, oh, what I'm going to do is I'm going to call this the first floor, this the second floor, and then I'm going to put a mezzanine here between 2 and 3, and I'm going to put another mezzanine here between 1 and 2. It's a sick thing to do, but not. I'm sure there are places, you know, I'm sure Guggenheim has considered buildings like this, right, in various places. But you can do that, and you see far away this is identical to B. Far away everything's the same. I have the same number of floors on this side as I have on that side, right? The average orientation goes around the same way, right? The average orientation of the layers goes around in exactly the same way as here. But now, it doesn't take a lot of imagination to imagine taking this mezzanine and pulling it back. I'm going to retract the mezzanine around the curve. And then, without too much ado, I'm going to pull the mezzanine up so it's next to the other mezzanine. Okay? So what had I just done? I had something where I had one flip, right? I rotated around by pi, and I smoothly connected it to something where I rotated around by pi, and I've added 2 extra floors. Mezzanine 1 and mezzanine 2, mezzanine A and B. Of course, I could do it again. I could add 4 mezzanines, or 6, or 8. I can also remove pairs of mezzanines as I like. This follows just because these two things are in the same conjugacy class. Right? It's only because the group's Nonabelian that I can do that. So we were kind of jazzed about this. This is work I did at the end. I'll show you pictures like, wow, it's Nonabelian, that must be what it's all about. And maybe we can understand the system this way. And this is a bold result. But we came upon this other result by Honar. And here, you can read it. I'm not going to read it out loud to you. Right? But this was the result, which was strange to us. The result was that if you have measured, so I think measured means that locally it looks like a smectic. Locally it looks like parallel lines. If you have measured line field, then you can have a defect like that, like a bullseye. A bullseye has charge 1, disclination charge 1. Right? The vectors, the layer normal rotates around by that. You can have the half, the flip we just talked about. You can have nothing. You can have one where you have a negative index, this negative a half, negative 1, negative 2, sorry, negative 3 halves, and so on. You can have any negative one you liked. You can go as negative as you like, but you can only go and stop at +1. And we just didn't understand that because remember how I emphasized when I looked at the pneumatic how I could bring the defects together? And I could bring them together and I could just add the charges. So somehow now I can't even add the charges, which would be okay. If I couldn't add the charges in both directions, I would have been alright. Okay, it's complicated, it's group theory. But I can add in one direction, but I can't in the other. So we didn't understand that either. But then, I remember the day, I remember it vividly, like it was yesterday. It was probably like 3 years ago today, that we realized the right way to solve the problem, the right way to think about it, and which allowed us to do other things, which I hope I can tell you about. So, here's my XY plane. My 2-dimensional Smectic is going to live in this XY plane. And I'm going to put on top of it phi of xy. Now, everything I've told you up to now is saying, look, I'm going to describe the Smectic as level sets of this phase field, this field phi. So phi of xy equals 0 is the first layer. Phi of xy equals 1 is the next layer. Phi of xy equals 2 is the next layer. But if I have a field phi and I'm in low enough dimensions, I can just draw phi. Right? And here I've drawn phi, and now I can just take sections. Right? So I'm just taking sections at different heights. Now I have a new coordinate. Phi is the up coordinate. And I look at the paths projected down onto here. Okay? And so, not surprising, we realized quickly, it was Brian Chen who knew that this was Morse theory. Right? And we could understand everything by, and when I was we were at the Institute for Advanced Study last year, and there's a little shrine to Morse. There's a picture and there's some sort of strange sculpture. So we go and talk about it in front of that. And we realize it's, for us, in our way of thinking, it's just about maps. So we said, look, what's a smectic? A smectic is just a topographical map. Every topographical map that you get from the U.S. Geological Survey satisfies all the rules that smectics have to follow. Two lines can't cross if they haven't already crossed. Sure, they can cross like this, right? But 12,800 feet and 12,900 feet never cross, okay? And they never end. So you see, it's just like a smectic. I never have to worry about, locally it always looks like a smectic, and the lines never end. It's just, it has all the rules I want.
So are the lines here equal altitude, the curves that run tangent to the molecules? In the analogy, if I look at a smectic and compare it with this map.
I don't know, no, they run perpendicular.
Exactly.
Moreover, when you look at the map, without knowing anything, without having the altitudes on it, you know where the peaks are. The peaks are places where you go around, right?
So if the molecules had arrows, they would sort of be the gradient field.
Precisely. It's exactly right. And so the molecules are plus or minus the gradient field, right? Or you can construct a secondary tensor out of it. So, without knowing anything, as I was saying, without having any heights, just looking at the map, you can discover where the peaks or the basins might be just by looking where you go around. Agreed? Okay. Of course, between peaks, there are always passes. I think there's a theorem to that effect. Okay? I think it's called the mountain pass theorem, right? So look, suddenly to us it became perfectly clear what was going on, at least for us, in our simple way of looking at it. We said, look, +1 defects are mountain peaks. I can't bring two mountain peaks together without pulling a pass in between them. And a pass is exactly a -1 index thing, right? If you look at how the director or the normal goes around, it runs around -2 pi as you go around clockwise. So it was nice for us because now we could understand why always you could have -10. You could have -10 because you could have 10 mountains surrounding a magical single point, which is the pass into 10 different valleys. It's not usually like that. Usually it'll degenerate into lots of passes, but that's possible. But it's impossible to take a peak and add another peak to it, right? That's as high as it goes, right? And so Honar's theorem to us was just a simple height function view of things. Now, is that everything? It's obviously not everything, because I haven't told you about dislocations where I get extra layers. I told you things don't end, right? So how can I do this if things don't end? How can I get extra layers in there? The answer is, anybody? You can try. This is how we do it in physics. We ask questions.
Extra layer.
How would you do it?
Why don't you try saying the question again?
Okay, how do you make lines end? What's one way to make a line end? Or to add extra lines? I'll give you a hint.
Well, you could have a monkey saddle, for example.
Well, monkey saddle wouldn't have extra lines. I want to now add like a dislocation. So I have layers. I want to add a mezzanine. I want to add 2 new layers.
Cliff.
Cliff? Kind of. Almost a cliff. A cliff would be a bad singularity, right? I have to make these smooth enough, I guess. I don't know what enough means. I don't know what smooth means either. Together. The trick is that this thing, this map, the height function is living on the real line. But in fact, I told you the height function lives on S1. So if I instead had maps, topographical maps, on things that were periodic, a periodic mountain range, periodic in height, then actually I'm going to be able to have defects, okay? Moreover, this is something that we want to emphasize. Somehow, even though I tell you that there's this phase that's telling you which set you're on, I have to give you more information. To tell you where I am in my order parameter space, I have to tell you the phase and its gradient. I have to tell you which way it's pointing. So this is the one-jet space. Really, I should be keeping track of something more complicated than phi. And when I do the intervals, I have to keep track of both of those things. And there's some consistency condition, right? As I go around in the xy plane, the gradient of phi tells me how phi changes. And so I have to respect that. So here are these edge defects. What do they look like? I'm going to show you a picture of an edge defect. This is the mountain range of an edge defect. It's a completely impenetrable picture, okay? So you couldn't possibly know what it is. I'm going to show you from the side. I have a set of planes, and I connect the planes. So each of these planes is parallel to each other. Each of them, when I take level cuts of them, are going to give me the same smectic. And now what I do is I connect one sheet to the other sheet. Okay? And so it's just a spiral or a helicoid. And now I'm going to take level cuts of the helicoid. You see it? So this is a level set of the helicoid. And so lo and behold, there's the dislocation. Right? And watch. You see how the layers are connected? You see the connectivity? This is the point where, oh, I can't reach it. This line was connected to this line, and this one was connected to this one, and then they swap, right? And the connectivity changes. Okay, you go down, and there it is. There's the dislocation. I've added 2 layers. So I'm allowed to have extra layers, or add extra layers, if I do the thing in a periodic box. Right? And I have to do that. That's the right thing to do. There's other things which Herman already brought up. If these things are vectors, then I know which way they point. If they're lines, I don't know which way they point, and so phi and minus phi have to be the same. Right? So, in other words, at least the way I see it, I'll draw the picture. Here's the picture. Here's one ground state. I take slices of it, I get these lines. I can do that, that's the same ground state. But I can also have ground states tilted in the other direction. They'll give me the same answer. For me, I think of it as, I showed you Mount Rainier, but that could have been Lake Rainier. Right? If I didn't put numbers on the topographical lines, on the heights, on the lines, then Mount Rainier and Lake Rainier would look the same. And the thing is, I have to be able to switch between one and the other, because there's an extra discrete symmetry. Right? The phi goes to minus phi symmetry. So it turns out that if I were to draw the space that wrong button. There you go. If I were to draw the space that the things lived on, right? So phi, right? Phi goes to phi plus 1 as a symmetry. Phi goes to minus phi as a symmetry. So phi actually lives on S1 mod Z2. But it's a funny mod Z2. It's not RP1, right? It's S1, they're fixed points, where I identify things across. Right? This and this is identified, and then there are these 2 fixed points. Those fixed points control where these layers can cross. Right? Otherwise, I don't have a nice description. So you can talk about and think about various kinds of defects. For instance, that flip that I keep showing you looks like this. You see, it's part of a cone and part of a set of cross planes. And the crossing, even though it looks like there's something horrible at the place where it crosses, that's at one of these fixed points. So I don't see anything when I go through there. It's completely smooth through there. The only place that it's sick is right here, where the cone pinches. And I can show you more of these pictures, which are just, amazing to watch. Okay. But I want to get to something else, which is why you're here. Right? So this is new, but I want to tell you which way we're trying to go. I'm trying to understand things. And for us, this was a giant, what's that word? Parade? Parade? No. This was an expedition into 19th century geometry. So, first of all, I had my layers. Right? These are the layers that represent the smectic. I have some surface. You can't see the surface. It's not there. It's in your head. It's in my head. Now it's going to be in your head. Here's the surface. To have things that are equally spaced in the xy plane, the surface wants to always make a 45-degree angle with z. Right? That's right. Because then the layers are going to be equally spaced. So if that's true, if I imagine an arbitrary system and I ask which structures can I get that are equally spaced in the xy plane, the surface that generates them, which has this normal, the normal always has to lie on, I don't know, what what is this, the Tropic of Cancer, the Tropic of Capricorn, it has to lie on something, the Arctic Circle, okay? Which means that that surface has no Gauss curvature, right? Because the Gauss map never sweeps on any area. And so that means that I can either have pieces of the plane or pieces of cones, and that's it. And I can glue them together. So the only equally spaced structures are this one, and this one. Right? If I want to have a negative charge, there's no way to have something where the direction or the orientation goes around by a negative amount, so that I get minus 2 pi, and also have it be equally spaced. So here's a nice way of showing it. What we want to understand is, what about 3 dimensions? What about that ellipsoid? What about 3 dimensions? Can I make a similar construction? Everything I've told you works in 3 dimensions. That is to say, now I have a function phi of x, y, z. Level sets of phi of x, y, z give me planes, surfaces. I have now a 3-dimensional Smectic. These are the real materials. These layers, they wobble, they wiggle, but they like to be equally spaced. So now I can ask, what are the equally spaced structures there? And can I classify them the same way? So I might have thought, oh, why don't I just do exactly the same construction? I know that the normal to that surface wants to always have an angle with this extra dimension. So instead of having the Gauss curvature, it's the Gauss-Kronecker curvature. What do I know about structures which have vanishing Gauss-Kronecker curvature?
Can I ask you a question about
Yes.
physics? So, in the physical material that you're looking at,
Yes.
the crystal, what are these layers that you're discussing here?
Oh,
math-wise?
so these are layers, so you have, instead of just one row of parking, you have an entire 2-dimensional surface of parked cars, and they have another surface below them and below that too. It's a parking garage.
So it's sort of an integral surface to the transverse two-plane field.
Exactly. That's exactly right. So the question is, can I tell you something? Can I classify all the equally spaced structures? All right, just like I just did right here. Because those are going to be especially low energy. The system likes to be equally spaced. So, this is very old.
Can I ask,
Yeah.
does this surface have to be perpendicular to the molecules or just transverse to it?
Well, it's the same thing that Steve asked. It can be either. If it's transverse, it's usually at a fixed angle.
The reason I ask that is if it's required to be perpendicular, it's unlikely to get these surfaces.
Which ones?
If the transverse two-plane field would typically not be integral to surfaces.
Absolutely. That's absolutely. Yes, that's the whole thing with Smectics, right? That's exactly right. The layers are more important than the molecules. The molecules become aligned to the normal of the layers. If you throw in the molecules at random, you're not generally going to get layers. Absolutely. So the system organizes itself, right? Okay. Oh, okay. So I was going to show you real pictures. So here are real Smectics. Like Rob said, these are sections of things that are obviously ellipsoids, right? Because here's an ellipse. There is a cross through the focus of the ellipse. Here's another focus. If you look really carefully, these ellipses are all tangent to each other. Also, all these ellipses are tangent to hyperbola. Okay? Here's another picture where I'm showing you an ellipse, and going through the ellipses are these lines. If you're very careful, you will see that the lines are also hyperbola. In fact, these are confocal conic sections, a hyperbola going through an ellipse, and they go through each other. So, 1910, Friedel saw pictures like this, all right? Micron-sized pictures. Saw pictures like this, and he said, you know what? This must be a set of layers. This must be microscopically something with layers. How did he know that? Right? I'll show you. So we realized, after a while, that this surface description, going back to 2 dimensions, is actually sort of very natural. Here, imagine I have 2 + 1 defects, and here I have these lines coming out, and here are the cones that generate these 2 structures, right? And eventually the cones crash into each other, right? The cones make equally spaced layers, because these are constant angle surfaces. They crash into each other. If this were light or water waves, you get this beautiful interference pattern. You could spend an entire semester of sophomore physics studying. Or you could spend a week learning about cosine. Real Smectics aren't like that, real smectics, the layers end, right? It's material. This is actually stuff. So this isn't like, this is like two wasps trying to build layered nests, and then suddenly they crash into each other, and they crash into each other on a line. Now they crash into each other on a line because they started at the same time. Okay, and you can see nicely, these two cones, because they have the same slope, always intersect on a plane, and whenever a plane cuts a cone, you get a conic section. There it is, there's the hyperbola, there's the other piece of the hyperbola. When I project it, I get a straight line. But what happens, first of all, if the cones start at different heights? First of all, I need to throw away the top part. I'm only going to look at the bottom part. Here are the cones. I have equally spaced structures. Again, they intersect on a hyperbola, but now it projects to a hyperbola. So two sets of concentric circles can intersect on hyperbola. This is what you would see in a microscope. In a microscope, what's happening here, right? The molecules are perpendicular to these blue lines. You have a place where the molecules are rapidly changing their direction. And that's what light scatters off of. Light doesn't scatter off things that are always the same. Light scatters off of places where there's inhomogeneities. So what you see in those pictures is you see these red lines. You see these focal lines that came out. So here we go. So whenever I have concentric or equally spaced layers, of course the equally spaced layers start at these two point defects, but then they can crash into each other on a cusp, but the cusp has to be a hyperbola. Also,
Why?
who said why?
The intersection of two quadrats should not be a hyperbola, it should be an elliptical.
Exactly. It could be a hyperbola. That's when these 2 points, if you excuse my language, are space-like separated. But those points can also be time-like separated. I'll skip this.
Oh, that's space-like.
This space-like. Let's go to time-like.
That line's gonna be horrible. Keep going.
Come on.
Keep twisting it.
Go to time-like. Here, I have two cones. One cone's pointing up. One cone's pointing down. What's left over is like a volcano.
All your red curves are conic.
Absolutely.
They're of degree 2. They should be degree 4.
Well, these are quadratic.
You must be assuming some special symmetry to get it to be degree 2. If you take two cones and intersect, you have a curve.
They're two cones that have the same slope. They have the same slope.
And they're sort of parallel to each other.
I don't know, phi minus phi naught squared minus x naught squared minus y naught squared equals 0. And then the same thing where I change 0 to 1. But they have exactly the same structure. So is that the extra symmetry?
Yeah.
Yeah. And so that's right. So as I said, because the cones, I said that I think, because the cones have the same slope, their intersections are on planes. Lie on planes. So then that's special. And then I get conics. Okay. But of course now I can do a Lorentz transformation to this one. And when I do that, lo and behold, this thing becomes an ellipse, and I get a projected ellipse. And that's another thing. Suddenly, this is cool, because I used to have just one special funky point, one focal point. I still have one focal point, but it's also generated a closed focal line. Now, just thinking this way, you can take the sets. You can either view these whole structures as being generated from the two focal points or this focal line. These are conjugate focal sets. Every point on this red line is null separated from these 2 points. And the only points that are null separated from every point on this red line are those two conical apices. So it's kind of cool. You can either talk about the 2 points or this focal line. Those are the things that you observe. In 2 dimensions, there's nothing else you can do. You have points and lines. What about 3 dimensions? So in 3 dimensions, I can take everything I've done and I can rotate it around a line of symmetry. If I do that, then I get concentric spheres intersecting on a plane. Here are concentric spheres. This sphere starts in a funny place compared to that one. And you get an ellipsoid that separates the two.
So all the time you're showing us pictures of surfaces, we should imagine the molecules of the material sort of roughly perpendicular to surfaces.
Absolutely. Right? And not only that, the molecules laying on the surfaces. And in between, there's less stuff. Or different stuff. So it turns out, and this is how Friedel figured everything out, in 3 dimensions there's one other thing you can do. In 3 dimensions I could have, so in 2 dimensions point focal sets and generate line focal sets, and vice versa. In 3 dimensions, point focal sets can generate surface focal sets. I just showed you those. They're the surface focal sets. But the other thing that can happen in 3 dimensions is I can have one set of lines and another set of lines. Right? Apparently, Friedel must have learned this in high school or college or something. Okay? It's very easy to show. In fact, using our language with Lorentz transformations, it's very easy to show that this is the only thing you can have when you have two focal lines in 3 dimensions. So this is a picture of 2 focal lines. Every point on this ellipse is light-like separated, null separated from every point on this hyperbola, and vice versa. This hyperbola goes through the focus of the ellipse. This ellipse goes through the focus of the hyperbola. They're in perpendicular planes. Right? This is very easy to see, and okay. It's very easy to see in our language. You have 2 sets. Phi squared minus x squared is r squared, and y squared plus z squared is r squared. And this is the set also y equals z equals 0. This is one set. And here's the other set, phi equals x equals 0. These 2 sets are null separated by construction. What do these 2 null sets look like? Well, this looks like a circle, and this looks like a line that goes right through the center of the circle. Right? This is in x, y, z space. Right? I have to drop phi. So, here's the structure. Every other structure is a Lorentz transformation of that structure. Right? I can fill this in. So, I can now draw concentric tori around this. They're equally spaced. The tori eventually crash into themselves. They crash into themselves on these cusps here. And every other picture you can see of this is just a Lorentz transform of that. And that's what this is. And these are the Cycloids of Dupin. Right? Or, it was strange. When I was in Britain, they called them Dupin cycloids. Dupin cycloids. And every time I said Cycloids of Dupin, they looked at me. Right? So I should tell you that the world of liquid crystals was dominated by the French. Right? Or in the early 1900s. And that's why it is the Cycloids of Dupin. Right? And not the Dupin cycloids. Right? But this was, Michael Berry and those guys, and they cycloids. That's what those are called. So these are these beautiful structures which degenerate onto hyperbola and ellipses. And that's what the picture here is. The hyperbolas and the ellipses. So, apparently Friedel, when he saw these pictures, remembered this. And he said, oh, it must be layers. The reason you're getting these must be because microscopically you're trying to pack layers equally spaced. So these structures are exactly what you see here. And these are called focal conic domains. Right? And that's generically, in those movies I was showing you, that's what we were seeing. That very first picture where all those pieces of ellipses, that's what you were seeing. So, what do we want to do? Well, so in a way we've classified, not by our original program. The original program was looking at zero Gaussian curvature surfaces. Right? I said when k was 0, I could tell you what all the equally spaced structures were. Here we did something else where we sort of built them using special symmetries of the Lorentz transformation to get all the equally spaced structures. Question is, can we do this? Is this everything? I don't think so. I know we can cut pieces of this out and glue them into other things. So there have to be some set of rules or some set of smoothness conditions that we need to say this is everything. Because I can always pluck pieces of this out and glue them into other things. And then we'd have the layers fit together. The other thing is that we want to talk about whole 3-dimensional crystals. Everything I talked about was smectics. Smectics are, if you like, the simplest crystal. Right? They're periodic in one direction, but not in the other two. Right? A crystal's periodic in 3 dimensions. So instead of having maps onto S1, a regular 2-dimensional crystal, the tiles here on the floor, you can check. after the talk. The tiles here on the floor can be described nicely by, their locations can be described by, or a point in them could be described by a point on the torus. And if I have three-dimensional crystal, I'd use the 3 torus, T3. This is the simplest one. It's just S1. And you can see just by having these funny problems of these discrete symmetries and by having to follow the jet space, I already have a much more complicated structure when I look at how the defects mix with each other. So how do 3D crystals work? Do you see this? Somebody once asked me, is this a real picture? Okay, well what do you mean? Yes, it's a real picture. It's absolutely true. But it's a photograph of a real piece of space, okay? It's an actual photograph of a real part of the world. How's that? Okay? This is a person. That's a crystal, right? This is somewhere in Mexico, somewhere deep in Mexico, and I mean that, deep in Mexico. There are these caves, the Nika caves, I think. So these are caves where they were mining caves. And they went in here, and one of the key things about mining is when you go down low enough, you know what you find first? Come on, it's nice. Water. First thing you find is water. So they have to always pump the mines out. Okay, they pump the mines out, and they pumped the mine out, and they found this. They had found this thing that was growing, perfect calcite crystals that were growing for gajillions of years, okay, making crystals that are 30 meters big, all right, solid crystals of calcite. Now, this room, which used to be filled with water, right, is 110 Fahrenheit, okay, that's 40 centigrade, more than 40, 42, right, and it's 100% relative humidity, because that water wants to come back, okay? So you can't actually live in there for very long, right? As my grandfather would say, you would holish. If you were standing in there for too long, you'd holish. And what is it? What do you have to do? You can be in there for about 5 minutes, or they can have special breathing apparatus. But there are these three-dimensional crystals. Three-dimensional crystals now, what do we get? Instead of having S1, I have to do T3, and then I have to mod out by these space groups of a real crystal. But I showed you when I mod out by, say, the Z2, it's not so simple. I'm just not making something that's, I guess the fancy word is I'm making an orbifold out of it, right? Because they're going to be fixed points.
GPUs is because you expect it to be triply periodic.
Exactly. Crystals triply periodic, and then I have to mod out by discrete symmetries, but they're going to be fixed points when I do that. And that's going to make it complicated. So, that's what we've been trying to learn. Here, I worked with these 3 brilliant people, Gareth, postdoc, Brian Chen, Gareth Alexander, Brian Chen, student Sabeta Matsumoto. All 3 of them we spent last year at the Institute for Advanced Study in quiet isolation from everybody, just studying these things. So, thanks for your attention.
So, Randy, we'd be delighted to answer questions. By the way, if you think of questions later,
Yeah, I live here.
that he lives here, and his email is his last name, Kamien, Kamien, @physics.upenn.edu.
You don't even need at physics. Just at upenn.edu. Huh?
What happened to physics?
No, you just, for $1.50 a month, you can get at upenn.edu. You can have Denagi at upenn.edu for $1.50 a month. Right? And you wouldn't even have to pay it. It would be your
But when I email
department
physics,
chair.
it gets to you.
Oh, yeah, physics, SAS, all those things, right?
Can I buy Donagi at?
Sorry?
I can buy Donagi at math.
Yes, that's the other thing. You can buy Denagi at upenn.edu.
Yeah, that sounds good. Yeah.
And then you can auction it.
Sure. Yeah.
Right.
I can start sending emails. Right.
Exactly. Exactly. Well, I'd be happy to talk if anybody has questions.